My name is Xinyuan Duan, and I'm a sophomore from Eastside Preparatory School in Washington State. My research topic is optimizing disaster impact detection pipelines. To give some background information about my project, natural disasters are happening more and more often, a recent example being the earthquake in Turkey and Syria. Real-time data is crucial to first responders, and a key part of that is monitoring building damage. A faster prediction for building damage would allow first responder to act quicker and reduce the number of injuries and deaths. So this research aims to reduce the model complexity of current existing research to achieve a faster prediction of damaged buildings. The data in this project comes from the XView Challenge website containing satellite images with the intention of detecting all buildings in various states of damage. The dataset includes 6 different types of natural disaster in 15 different countries, and some examples are earthquake, flood, volcanic eruption, wildfire, and more. The data contains many pairs of images, and each pair has pre- and post-disaster image. The images have a resolution of 1024 by 1024 pixels, and each image contains multiple buildings. The images also come with labels. Each building in the image has a polygon and a damage type label. The polygon label represents the shape of each building, and there are 5 different damage types that are listed here, and each of them were encoded into their corresponding number during the data loading process. My hypothesis is that a bounding box detection plus semantic segmentation approach would be best to tackle the research goal. The reasons being, buildings are generally shaped as a box, so the model can achieve a high accuracy with bounding box detection, while the normal polygons require a lot more computation, and the number of vertices would have to change depending on the shape of the buildings, which require a more complicated model. Model complexity is a key concern due to the standard approach of semantic segmentation labeling each pixel, and this becomes especially relevant on satellite images, which tend to have extremely high resolution. So this research proposes that instead of classifying every pixel, the model should classify each box to reduce the number of computations and simplify outputs into bounding boxes along with damage types. Since this research intends to use bounding boxes, the ground truth polygon labels need to be converted into boxes. I assume that each image would contain 64 buildings at most. So my transformed data for boxes would be an array of size 64 by 4, with 64 being the number of boxes, and 4 being the x minimum, y minimum, x maximum, and y maximum coordinates. The damage type data is simply an array of 64. If there are less than 64 buildings, the extra values for the box array are set to 0, and damage type are set to 1, which indicates no damage. My model is a convolutional neural network consisting of 5 convolutional layers with max pool and ReLU activations and 3 fully connected layers after. The model has 2 outputs, prediction for the box coordinates and prediction for the damage type for each box. The box prediction will be 64 by 4, which represents 64 boxes, each with 4 coordinates. The damage type prediction will be 64 by 5. The 64 again represents the 64 boxes, and the 5 values are the possibilities for each damage type. The damage type with highest possibility is chosen to be the actual prediction. This output structure is designed to accommodate for the fact that each image has multiple buildings. For the loss functions, I used complete box intercept over union loss, also known as CIOU loss, for the box predictions, and cross-entropy loss for the damage type predictions. CIOU loss works better than normal IOU loss in this case because it adds an additional penalty when the boxes do not overlap. It also considers important geometrical factors such as overlap area, normalized central point distance, and aspect ratio. In the training process, I tested many different values for 2 hyperparameters to see how they would affect the model performance. the two hyperparameters being learning rate decay and training epochs. The top three best performance are shown on the slide here, with the highest accuracy being 62.6%. This shows the evaluation loss for both box prediction and damage type prediction for the model that has the highest accuracy. As you can see, the loss is generally decreasing as the model trains on more data. The result is that the model achieved an accuracy of 62.6%, which is lower than expected. Possible reasons could be that first, input images having more than 64 buildings. As shown in the image to the right, it clearly has way more than 64 buildings, which means that during the training process, the model couldn't fully capture the data. Second, perpendicular boxes are not accurate enough, especially when buildings are slanted. Third, the model design might not be the most effective. I recognize there are limitations in my research. For example, I wanted to have more than 5 convolutional layers in my model so that it can have a better accuracy. However, since I was using a free Google Cloud virtual machine to train my model, the GPU did not have enough storage to afford a more complex model. So in conclusion, the bounding box plus semantic segmentation approach has potential to become accurate and effective if improvements are made. Future work should focus on improving this model, such as having variable output length and trying out models like YOLO and SSD. Thank you for listening. Any questions?
Awesome. Thank you so much, Xinyuan. I'm curious, can you talk a little bit about just your interest in this topic, sort of what led you to wanting to study this?
Yeah, so I'm personally really interested in like environmental science and like just environment related things. Like I'm part of my school's environmental club. So I wanted to do something related to environment. And since I also have a strong interest in like machine learning and neural networks, so when I came into Polygence, I wanted a project that can use machine learning to solve environmental related problems. And so that's why I found this building damage detection project. I think it's really beneficial because like it relates a lot of the real world issue that's happening.
Great. And so just for everybody listening, or the attendees, feel free to drop a question in the Q&A section at the bottom of your screen. One question that I had as you were presenting, so you mentioned that one possible use case is to help rescue personnel in disasters. Do you know if anything like this, this modeling exists today?
Well, I think this kind of modeling definitely exists today, but from like the literature I know, most of them use semantic segmentation approach for this type of like computer vision stuff. And I think semantic segmentation is very slow because like it has to classify every pixel. So going into this project, I wanted to make the models faster.
And the last question I had for you was about what was the hardest part of this research project for you?
Yeah, I guess the hardest part is definitely learning about neural networks because I think it's a very complicated topic. And to be honest, I still like don't fully understand everything because the math behind it is so complicated. Like my current knowledge level wouldn't allow me to understand it fully. So that's also another reason why I didn't use any pre-built models in my project, because I wanted to learn to build a neural network model from scratch on my own. Another challenge is definitely data processing because I downloaded the data from the XView Challenge website. It comes in like very messy formats. So I had to do a lot of cleaning and like reshaping the data to get it into the format that I want.
Can you actually talk a little bit more about that? Because this is actually a pretty common issue with a lot of publicly available data sets that the data cleaning process is actually a bit tedious. How did you go about that process of cleaning the data so that you could build the models?
Yeah, so I think a good first step is to actually manually open the data, like the JSON file or whatever file it came in, to look at the data. I actually have like a document and I have like highlighted different parts of the data that I want, and then I can like look at the data, the structure of the data, and to see how I would like separate the data I want from the data I don't want in code.